Good morning, everybody, and thank you to Mikhail and the organizers. I drive by the Getty every single day on my way back to Pasadena from UCLA, and I'm always reminded that I need to get up the hill a little bit more often. When I stepped out of the parking structure, I am always reminded of what a beautiful place this is and what tremendous resource it is for the community. And so it's a real pleasure to be here to talk to you all. I was looking at some posters out in the session and obviously was reminded of the fact that almost everyone in this room is going to be pretty familiar with a lot of the technology that I'm talking about. But what I wanted to try to do today is to make sure that people understand that, like Shant was just describing in the last talk, that sometimes when you can't buy it, you build it. And sometimes we want to make equipment do things it wasn't designed to do, or identify challenging problems and push in new directions. That doesn't always happen overnight, but it is something that this community, I think, can benefit from by continuing to push forward. And so the slide that you see here is introducing the topic, which is atomic force microscopy. I saw a lot of nano indentation descriptions out in the lobby, and I'm going to talk about some of the more recent advances in AFM and how we can sort of bridge that gap between the limits that we found in the past and where we may be able to go in the future. So similarly, I'll just introduce you. So CNSI may not be familiar to you all. I believe there's an opportunity for some folks to come down for some tours. We actually have an open house tomorrow. But the CNSI is the California Nanosystems Institute. I'm at UCLA, which is just down the road, less than 2 miles from here. And so for anyone interested in coming to see, I think there's some lab tours signed up for tomorrow. We do have an opportunity to attend our open house. But basically, the CNSI is a research institute funded by the state of California, private industry. It's a partnership with the University of California, Santa Barbara, and UCLA. It's not an academic department. We don't have a degree program, but we bring investigators together from different disciplines to solve interesting problems in team science. And so we do basic discovery with an eye towards, challenging problems, but ultimately also to incubate new technologies, to commercialize them, to get them out into the wild, to benefit society, and to train the next generation of scientists and engineers, which is part of our role as an academic research entity. And so the quick background, and I won't belabor the point here, is to say that we do basic discovery in all domains of nanoscience and technology. We have a broad collection of technology platforms, which is some of the things I'll highlight a little bit today, and what it would be made available for anyone who wanted to come and visit, certainly tomorrow or anytime, which are open access user facilities focused on making and measuring things at sort of the limits of resolution and scale. And then, of course, as I mentioned, a lot of the work that we're tasked to do is not just to make papers in nice journals, which of course is always a wonderful output, but to take those research innovations and get them out into society through commercialization and translation. And so we do have a technology incubator that houses around 30 startup companies, some UCLA affiliated, otherwise is sort of the active place where entrepreneurship happens at UCLA. But that center pillar, which I mentioned, are our technology platforms. And so this is a collection of 6 user facilities. They're open 24/7, 365 days a year. I mentioned to Lorenzo, who's going to be coming to the Getty, that these resources are available when he comes here. They're available to anyone. And so we have thousands of users from all over the world. Of course, a critical mass of folks come from UCLA. But if you see anything or are interested in anything, these are totally open to anyone. There's no priority or anything along those lines for anybody. We want to solve interesting problems, and we do this at a pretty impressive scale in terms of the capacities that we have. You can see on the right the things that we have. Obviously, we have a lot of characterization, fabrication, semiconductor material growth, a large collection of facilities. It occupies about 90,000 square feet of our building, so it is a pretty robust platform. But what I'm going to highlight to you today, based on the title, is one of those facilities which focuses to some extent on mechanical characterization. And so this isn't lost on this audience. I use this slide when I teach my students, particularly an undergrad course on microscopy, about the differentiation between optical and electron microscopy-based techniques versus the scanning probe technology, which is that we understand the physical properties and the structural properties of the world around us using our senses. All of you currently are looking at me right now. Photons are bouncing off of me and being collected by your retinas and integrated in your brain to generate 3-dimensional representations of the space around you, right? And we get spatial and structural information generally through our sense of sight. Add some fancy layers of technology on that, lenses, lasers, electron beams, and you can imagine that you can push the limits of resolution using these far field detection methods. Now, of course, we have other senses at our disposal, but we as humans don't get a lot of great information about structure or space from our sense of taste, our sense of hearing. But one that we do have at our disposal is our sense of touch, right? And whether we're blind or we have the benefit of sight, we can learn a lot about the world through physical interaction, through this tactile sort of direct feeling of material properties. And so the example that I usually give is I'll ask students, I'll say, describe that to me. What is that? Right? And they can tell me that, well, it looks like it's got, some interesting cleavage lines. It's orange. We know something about its electronic properties. It's translucent, so we have some indication about its structure, right? But until you physically touch it, right, you wouldn't know whether that's a piece of glass or a piece of amber, but it's actually a piece of Jell-O, right? And I always joke with them, we don't eat things in the lab, right? But nevertheless, the sense of touch, this tactile physical interaction, the capacity to push and poke and pull on things gives us insight into material properties that you can't gain just by looking at things from a distance, right? While electrons, optical techniques, far field measurements are incredibly powerful with resolution, spatial, temporal dynamics, there's an additional layer to understanding the properties of a material that come through interaction. And so what we do at CNSI, and this is where I actually met Michal and Vincent a number of years ago, is that we provide access and expertise and technology around scanning probe microscopy, particularly a pretty heavy focus in atomic force microscopy. We do scanning tunneling microscopy, other ancillary techniques, but looking at the mechanical properties of materials in addition to structure, topographic measurements, electrical, mechanical, all those sorts of things. But we push into these particular directions around nanomechanics. A lot of our work started looking at cells and tissues, early on looking at orthogonal methodologies to study the mechanical properties of biological samples. But we did have an email that I believe was facilitated through a long time ago, a guy who I don't know if he's ever around anymore, Giacomo Chiari. Giacomo and I met probably 15 years ago, and he was working and helping us with our Sci-Art program, which is the sort of educational program on the interface of science and art. He started asking me questions about, can we measure these interesting things, magnetic measurements of magnetite particles inside of paint taken from somewhere in Italy. And so we started having interesting conversations about what we may be able to do in different ways. And then I ultimately met Michal and his colleagues a few years later and said, well, what can we do with atomic force microscopy using the existing capabilities that were there? And I think this was probably almost a decade ago. And so what we ended up doing, the first entree that I had into cultural heritage materials was looking at the mechanical properties of Disney cells, right? So these are paints on plastic films, exposing them to different variable levels of relative humidity and looking at the adhesive properties of these paints, right? And the mechanical properties, and using the AFM as a methodology to quantitatively characterize the adhesion under different specific conditions to address the challenges of delamination and all the things that this community is very familiar with as you're trying to store these materials for decades. And so this work was exciting. It was quite interesting. It actually produced a manuscript in 2017, which was quite nice. But it did expose some of the real challenges that we faced in terms of what the microscope could do, what it was designed for, which was certainly not this type of measurement on a sample like this. Atomic force and scanning tunneling microscopes came out of IBM. It's the semiconductor community, right? And so the vision of what they would be utilized for is very different than the things that we're trying to use them for now. And so what we decided to do over the, what we continue to do is to figure out different ways to address challenges. And so many of you may be familiar with different modes of the way that the atomic force microscope or an imaging and nanoindenter can work, right? We have these challenges of being able to do quantitative measurements, right? Doing force distance curves, doing indentation measurements that are truly quantitative, but ultimately also providing the value proposition of an imaging system, right? And so at the time when we were working on this, what we had at our disposal was called force volume imaging. Pretty slow, low resolution mechanical maps, right? That we could go in and we could poke on surfaces, we can pull on them, look at modulus, look at adhesion, and get pretty low resolution because the methodology wasn't developed for speed or resolution. It was developed for just sort of traditional mechanical profiling. Over the last decade, right, there's been some pretty nice advances in being able to take that and speed it up while retaining resolution. And so some of you may be familiar with some of the terms that are used by the equipment vendors. Quantitative imaging modality where the tip is moved in a little bit of a different way to make it faster. Bruker in particular has a technology called peak force QNM, quantitative nanomechanics, that moves the tip again in a sinusoidal wave and actually can address some of these challenges. And they were really all geared around maintaining quantitation, but overcoming this speed limit, right? Which is that force volume mapping, while incredibly powerful and still the sort of gold standard to make sure that the measurements that we're doing are truly quantitative, has some real challenges in terms of speed. And in particular, we always want speed because we want temporal and spatial information to be available to us. The other thing that we had to think about, right, which is that the AFM originally was designed with these very sharp pyramidal indenters, right? They were designed to have atomic, it's called the atomic force microscope because it wants to be able to measure the forces between atoms, right? So the tips are designed to be incredibly, incredibly sharp. That's great for resolution, right? But that's not always the best for quantitative modulus measurements, as an example, right? All of the models that we use don't assume a pyramidal indenter. They assume a spherical indenter or a conical indenter, right? And so it's very easy for, you can plug in an equation for, using the Hertz model, but when the tip that you're using doesn't actually fit the model, or the indentation depth, the effective interaction volume is not actually mapping onto the model itself, you run into challenges. And so we've been working with the vendors and the manufacturers of AFM tips. We used to make them ourselves in-house, but to create new types of cantilevers, new types of probes that not only have the mechanical properties, but also the tip shape that allows us to address the mechanical properties of these materials. And so what you'll see on the lower right are tips that you would have never been able to buy 15 years ago. Mechanically dulled tips, intentionally dull, that have a rounded edge, right? Or even more recently, attaching colloids or spheres or electron beam deposition of a carbon sphere on the end of the tip. Or the most recent ones, which are just recently come out, are literally a silicon pillar with a quantitatively measured sphere on the end, so that the mechanical models that we can use when we're indenting soft samples actually matter and are reasonable to apply when we're trying to analyze our data. And so developing the microscope, developing the tips, has been an area since the last time we worked together that there's been a lot of change. The second thing, of course, is that, these schematics that you see in nice journal articles that make it look like the data is all beautiful, right? Every time you poke down is not representative of a reality, right? We are doing thousands of curves in many cases, and getting curves that you see here on the right, where you have to do a lot of work to understand, is that real, right? Is there some artifact there? Right? And so a lot of the additional work that goes into this is also developing software that can interpret the data and identify what is real, what is an artifact, what is an unexpected result, and why is it unexpected, to continue to allow us to be able to not just do single curves, but when we're collecting now curves at kilohertz frequencies, we're getting thousands and thousands of indentations per second. Right? We need to be able to analyze this data in real time and have the models that we're using to understand it be relevant. Right? And so there's a lot of stuff on these basic understanding of what it means to do AFM-based indentation. And the other part of it is, and what we learned from a lot of the samples from the cultural heritage community, which is that the big challenge is that the samples that these microscopes were designed for are super flat. If you take a silicon wafer, the roughness is a couple nanometers, right? You drop some molecules on there, you put an electrode down, some material for microelectronics application, they're very smooth. They're not designed to handle roughnesses on the orders of tens and hundreds of microns, imaging over large areas. And so another area that we worked on quite strongly was trying to influence the manufacturers to say, you need to rethink what this microscope is designed to do. We cannot continue to just take a microscope designed for semiconductors and try to apply it to biology or to apply it to cultural heritage materials. We need different capabilities. We need larger scanners, longer ranges. We need to integrate optics and overlay to combine multiple modes together. And so the microscope that you see here on the left is a microscope that we purchased from a commercial vendor, but we were in a long-term arrangement with them to try to identify how to develop the technology. And so what you see here now is an atomic force microscope that, instead of having a 10 micron range in the Z direction, has a 200 or 300 micron range in the Z direction. Instead of being able to scan a 100 micron area, it can scan 200, 300 and stitch and overlay, as you'll see in this image, over centimeter areas with sub-micron precision of the tip displacement. And so this is just a quick graphical grab of what happens in the microscope, where you are now integrating basically a tiled version of an optical microscope over a few centimeters right? And then being able to pick and place and pull and decide where you want to go to do your mechanical measurements, whether they're force curves, whether they're just images, or whether they're combined nanomechanical maps, right, over these large areas on very, very rough samples in many cases. And so this is an example from biology, and I'll show you because we haven't applied this new microscope to any of the materials you all are talking about. But you can imagine, if you let your brain go a little bit, that a tissue, right, extracted from a biological patient in the hospital is as equally challenging rough sample as what you would come to me with a piece of, let's say, painting or some sample of a stone, or as an example. And so what we are working on quite heavily now, and these are just two representative examples, is to take correlative measurements, right? So we're combining different technologies together. Next to the AFM lab, we have an advanced optics lab. We have an EM lab across the hall. And so doing multi-photon deep tissue imaging allows us to take samples that are tissues, right? So this is the simpler one. This is basically a microtomed tissue sample. But you can imagine that from an AFM, if you've used it before, this is not easy, right? This is a very, very rough sample. We need to be able to land on top of it, know where we're landing, and do measurements on top of it, not only for structure, but also mechanics. And so the example here is that when we have that, we can import and overlay our optical images in with our atomic force microscopy images, and then we can collect topographic maps as well as mechanical maps over these large areas. And so correlative measurements, where we're combining multiple modalities together, allow us to combine topography with mechanical measurements, modulus measurements on the local, and while retaining the spatial resolution down to the tens of nanometers. This sample had a surface roughness on the order of a couple hundred microns. So you can imagine now we're moving across 100 micron regions up and down while scanning over that image right there is just 100 micron frame in what was a much larger map. And so when we can imagine being able to take a microtome tissue, right, and now drop the tip down onto it and image it and be able to controllably indent that sample, then we think, well, what's next? We don't necessarily want microtome tissues. What's the next step forward? And so this is an example of a collaboration we have with orthopedic surgery, where they're taking bone samples to look at the attachment of bone to ligament in the knee, right? And they're looking for a specific thing called an enthesis, which is this region of attachment, and to probe its mechanical properties. And so if I didn't tell you what was on the left, you may not know that it's a biological sample. But what you know is that it's quite large, it's quite rough. It has roughnesses on the orders of several hundred microns. And so if you would have came to me with this problem 10 years ago, I would have said to you, there's no way we can look at this with the AFM. And if we could, we can look at a tiny little area before we start to bash into the surface. So again, we combine it with two-photon confocal to identify the region of interest. And then we can go now, and you can see on the left-hand side, the AFM sitting on top of a real view of the optical image that gets overlaid with the two-photon image to generate now a localized mechanical and structural map of the surface. And so this allows us to take and identify actually the region of attachment between tendon and bone and the formation of this region in the middle, which is called an enthesis, and to probe its mechanical properties, right? And so while these two examples are from biology, right, my point here is that you can imagine that the challenges are similar, right? We've got rough samples, we need large areas, they can be sticky, they can be soft, they could be hard, but now this new capability of new tips, new scanners, new microscopes, and the combination thereof allows us to take this 30-year-old technology and imagine moving it in new directions for different classes of materials. We're also pushing a little bit again and trying to make things do other capabilities. And so I saw a poster outside looking at DMA. Part of the area is that we're also trying to work with the vendors to say we would like to be able to do nanoscale rheology, right? Like giving us more control over how the tip is moving. And so in this case, it's kind of hard to see, but we have an advanced capability now to script the way in which our indentation profiles look. So we don't just say how long it is and how hard we push, but we can push and then we can vibrate and probe viscoelasticity, for example, do AC indentation while we're in contact. And so we have a lot more control in these new microscopes around what the force distance curve looks like to be able to probe those properties. And so I think with respect to the clock, I went a little bit quick, which is fine because it's open for questions, but I always point out the fact that I did very little of this work, right? And so the stuff on the left-hand side is a collaboration with Kristen Stearns-Reeder, who's in orthopedic surgery. She studies muscular dystrophy and cerebral palsy. Michael Lake is on my team. He's one of my staff scientists. He's the one that really drives the bus on making this microscope go in exciting new directions. And then the right-hand side, where you saw that work on the orthopedic surgical samples. And maybe I failed to mention, those samples were taken straight from surgery into the lab, mounted and measured, right? And so challenging samples, but it's exciting in the way that we go. And of course, all the folks that are here organizing, the people who I introduced, where I became introduced to the GCI 20 years ago, and the organizers for inviting me to come today. I wish I could have been here yesterday, but travel precluded that from happening, but I'm excited to stay around today. And by all means, if anyone has any questions now or throughout the day, I will be around all day and happy to discuss with you what we talked about and what the opportunities look like for you to take advantage of some of these capabilities, whether at UCLA or in your local neighborhoods. So with that, thank you very much.
Thank you very much for the very interesting presentation. Any questions from the audience?
Thank you, Adam. It's very interesting. I'm here.
Where am I?
At the end.
In the back. Okay.
So full disclosure, I used AFM in the past. And so one thing I know that when we were using it at UCL in London, one limitation that we had, let's say, with samples, the materials from cultural heritage, was that we wanted to measure like in situ on a real object, and we try on a violin, for example. So first you can see the issue with the surface that's not flat, but also like finding the way to stabilize the object, and also the sort of noise that would come from it. So one big issue was like to make sure the tip was stable, and we were not actually measuring movement from the object itself. So I wonder if in the development that are done right now, if there is, I know you can move those AFM heads, but the issue is still how to measure real objects and not just samples. Even if you increase the size of the surface that can be measured, how you can deal with that. And the second thing, I was wondering if you had a chamber to control the humidity when you're doing the measurement, because as you know, yeah. It's very important for us. Yeah. And what are your thoughts on that?
Yeah, so a few things. I think that the stability of the probe is always a challenge. Like one of the areas in the probe development that I didn't mention is that we used to use a lot of probes that had a metallic coating on them, which provides basically differential thermal expansion between the silicon and the metallic coating. And that was there basically just because our detectors weren't sensitive enough, right? Especially in a fluid environment, as an example. So a lot of the new probes have eliminated the need for that coating, because not only the probe design, but also the way in which the detection system has improved its sensitivity. So we don't have as many challenges there. But to your point, right, like we do, of course, and not just we, but these microscopes need to control the environment. They're very, very sensitive, right? So we have heating and cooling stages with feedback control. We have a humidity chamber and a small volume cell, but I just said small volume. The problem is that those humidity chambers are generally designed for a sample, that's yay big, right? When we did the work, we literally had an enclosure where we had a tank of nitrogen, right? And purged out the entire enclosure under overpressure, and then had a humidity generator to control like a huge volume, right? Like that is not necessarily sustainable. There's no fundamental reason why the microscope itself couldn't have a larger volume. Right? These things are just where there needs to be a demand for it. They're generally designed for smaller areas. Now, in terms of dealing with the fact that the AFM sits on a stage with an optical microscope, this is a question that Giacomo asked me 20 years ago. He's like, do you have an AFM that I can put on the wall, right, and be able to measure the properties of the wall, right? There's no fundamental reason why you can't do that, right? There is a mechanical challenge in terms of getting it mounted to the wall so that it doesn't move around and vibrate, because this is basically like the most sensitive vibration sensor you could imagine. But the physical configuration of some of the newer microscopes have basically a 3-point contact mechanism where you can put it on the table, right? Like I've imaged the table just for fun when we were testing it out. You can put it on all different types of samples. But there are, of course, stops and limits to that, right? These large areas that I was saying, they're enabled by the stage itself. They're not actually in the AFM head, right? So that big chunk that you may have seen on the bottom of the microscope, if I go back, that the development there on the long range is actually from the stage. And so it is designed to be able to have see if the laser works. So this whole thing is called the hybrid stage. The AFM head is very similar to what it's been. It's got some modifications. But this large area stage is the one, and it's actually much more than 20 by 20 millimeters. It goes 2 centimeters on the newest one. This is just a picture from Bruker. That is still a limit, right? So in terms of what samples you can move over, there's going to be a limitation there. We don't have the ability to move the tip over 2 centimeters. Again, with most things, I say you can't buy it, you build it. There's no reason why it can't happen, right? There's no fundamental limit. But in terms of what you can buy, those capabilities aren't, not all the capabilities that you're asking for are going to be available immediately. Sample prep is always the challenge with every characterization technique.
Lucas?
Can you hear me? Yes.
Yeah.
Łukasz Batasz, Polish Academy of Sciences. In my institute, there are groups working with the proteins, and we try to understand what's the adhesion between some proteins which are used in our field as a glue with the material. So we attach the proteins to the tip, and we try to look at different areas for adhesion. And it worked perfectly in the liquid, but when you go to the air, the charge is completely changed. How do you think it would be possible in a certain moment to measure the properties in the air?
It's challenging to deal with those sorts of things in air because, yes, in liquid you can screen out the ionic strength of your buffer, right? Screens out a lot of the short-range forces, electrostatics that are going to be very difficult in air. I mean, all of those measurements, I'm happy to hear that it worked perfectly because attaching proteins to tips and doing single molecule force spectroscopy is a non-trivial experiment by any stretch. In the air, I think that one of the areas that you can sort of play with is the relative humidity issue, right? Because you do have, to a certain degree, a sort of just capillary layer of water on everything at elevated humidities. It's something that a lot of people don't think about as controlling the humidity, but we see that in a lot of other measurement modes where, the tip is actually, even though it's dry, is actually in contact with water, right, at that surface, right? So playing with the humidity is probably the way that I would recommend thinking about trying it. There are other methods that you can do to try to minimize electrostatic forces, but when you're measuring the forces between individual molecules, those adhesion forces are on the orders of tens of piconewtons, hundreds of piconewtons. It's very difficult to remove the long-range effects without attenuating them, which is what the solution's really good at.
Other questions? Mika?
Thank you very much, Adam. I knew I will learn something very interesting from your talk. I love this concept of this machine, the idea that you can do the scan over like 1 or 2 centimeters area is I think, a game changer in our field. So I'll be very happy to look at it. I remember when we bought our IFM here at Getty, the only one we still have, it was super exciting up to the point when people realized that they can measure the changes in the surface over the 60 micron area. And if you modify them, you will be not ever in your life find the area you looked at before. So I think this is a major thing. And I would be very, very happy to look at this capacity. Thank you.
Yeah, I remember when you got your system, right? And I think that there's always trade-offs with whatever you buy, right? But a lot of it comes down to understanding what it is you specifically need. There's no one-size-fits-all solution for most of these things. And so one of the reasons I wanted to talk about this is to just point out that, yes, it's 20 years of development, but these systems are commercially available right at this point now. And I think that a lot of people in the community, we have a lot more action in the biomedical sciences, people looking at tissues and surgical samples, but I don't know that people are aware that this capability is there, right, for more challenging, non-biological samples. And so, all right, look at that, right on schedule.
Yeah, perfect.
Okay, thank you.
So let's thank once again Adam.